A z-score is a heck of a useful thing. Let's go over what it is and how to calculate it. The z-score of a data value x from a distribution of data with mean x bar and standard deviation s is calculated simply by doing the data value x minus the mean x bar and dividing that by the standard deviation. Oftentimes, the z-score of a data value will just be denoted with a z, but if it's important, we can put the data value itself in the subscript so we know which data value's z-score we're talking about. As you can see from the formula, the z-score of a data value just tells us how many standard deviations away from the mean it is. X minus x bar is x's distance from the mean. That's how far the data value is from the middle. And then when we divide that by the standard deviation, that tells us how many standard deviations away from the mean is the data value. Let's do an example of calculating standard deviation. Perhaps we have some big pancake eating contest, and John has eaten 12 pancakes. The average number of pancakes eaten in the contest was 16. And the standard deviation was 3.1 pancakes. Then what's the z-score of 12, the number of pancakes John ate? We could denote that just with a z or with a z12 to indicate specifically we're calculating the z-score of 12 in this data set. I'm just going to use z because really that's most common. The z-score formula, like we said, is to take the data value, 12, and then subtract the mean, in this case 16. Then just divide by the standard deviation. This is about negative 1.29, so the number of pancakes John was able to eat is about 1.29 standard deviations below the mean. Below the mean, since of course it's negative. Whether a highly positive or highly negative or close to zero z-score is preferred completely depends on context. If this is a pancake eating contest, then naturally people would want a higher z-score. They're eating more pancakes. They're placing higher in the competition. Here's some general facts you should know about z-scores. A bigger z-score, whether it's bigger in the positive or the negative direction, is a more unusual data value because a z-score is how many standard deviations away from the mean a data point is. So a bigger z-score means it's more standard deviations away from the mean. For example, a z-score of negative 2.1 would be more unusual than a z-score of 1.8 because negative 2.1 is bigger. Yeah, it's negative, but disregarding the negativeness, it's bigger. It's 2.1 compared to 1.8. It's further from the mean. Certainly, if the z-score of a data value is positive, then that data value is above the mean. If the z-score is negative, that data value is below the mean. You can use this to help you remember that it's the data value minus the mean. If the data value is below the mean, your z-score should be negative. And for that to happen, you need to do data value minus the mean. Make sure you don't mix those up. You should also know z-scores are unitless. The data value and the mean have the same units, and those are the same units as the standard deviation. So they cancel out, and the z-score is left with no units. Just tells us how many standard deviations away from the mean a data value is. Also, a data value's z-score is sometimes called its standardized value, but it's usually just called the z-score. One last point about notation. In this formula, I'm using sample notation, saying we have a data value from a sample, a mean from a sample, and a standard deviation from a sample. If, on the other hand, we have a population or a model that we're using, then it's typical to use Greek letters and the parameter notation. So in that situation, the formula would look like this. The z-score of a data value x is x minus the mean mu divided by the standard deviation, sigma. To finish off, here's a little practice problem for you. We have Alice and Bob's performances in two Olympic events, the long jump and the shot put. We know what the mean is for all contestants, and we know the standard deviation for all contestants. We want to know which performance is more impressive, and in order to answer that question, we need to calculate z-scores. We need to figure out how many standard deviations away from the mean the performances of Alice and Bob are in these events. Then, even though they're different events, we can compare the z-scores to see which performance is more impressive. Go ahead and calculate the z-scores. I'm going to put them on screen now. now. And there are the z-scores. You can see that Alice won the long jump and Bob won the shot put, but clearly Bob's performance in the shot put was not as impressive as Alice's performance in the long jump, because Alice's performance in the long jump was 2.7 standard deviations above the average, whereas Bob's winning performance in the shot put was only 2.51 standard deviations above the average. Still impressive, 2.51 is a pretty big z-score, but not as exceptional as 2.7. Let me know in the comments if you have any questions, and check the description for links to other statistics lessons.